and welcome to this manufacturing systems technology part 2 module 21. We would like to now see given this control chart and given some of the out of control points, can we really replot so that the process can show better control. So obviously the first thing that we have to understand from our discussion in the last module was that it is not it is obvious that the measurements made are not the result of constant system of chance causes. If subgroup 1 for example, which corresponds to a R bar falling out of range is eliminated from consideration, the R for the remaining becomes equal to 536 by 15, that is 36. So you are removing the 85 range which is out of the upper control limit of the ranges in order to replot. Okay. So this actually gives you about 0.0036 as the new R bar, which can again be, because the subgroup size is not changing, used to calculate the upper control limit. So in this particular case the upper control limit becomes 76 if you have eliminated the out of range point, the data point which was out of range corresponding to subgroup number 1. Okay. So obviously if we replot the system now, the upper part again would change because of that, and instead of this 0.0082 it would be 0.0076. So let us actually look into the chart and see what are the other outliers, and then we get rid of those outliers and then again try to replot. So as you know that in this particular case, as we had seen, the subgroup 5 falls exactly on the upper control limit of the X chart. So let us say this subgroup here, right here, I am sorry, this is not the one. So the subgroup 5 here falls exactly on the upper control limit, and it can be rejected because this is actually a very shady situation which can just about go across the limit for a little bit of process decontrol. So we eliminate this subgroup 5. So as the subgroup 5 is eliminated, the new range that can be computed is 460 by 14 now, and this becomes equal to 33. Okay. So an estimate can be made of sigma from R, obviously from control table, the corresponding 5 subgroup size, the sigma and R can be related by R by D2, but D2 value is about 2.362 from the control table. So that is 0.0014 inch, that is the sigma. So if I consider this sigma, so obviously the 6 sigma is about 0.0084 inches, and that is the natural tolerance or spread of the process, and the spread may be actually compared with respect to the tolerance spread, which is the upper and lower control limits sort of taken off from each other, which happens to be 0.0041 inches in this particular case. So what I would like to do now is that just because the new range happens to be 33 by eliminating the subgroup number 5 and subgroup number 1 because of their outlier properties, and also you can actually eliminate this subgroup right here which goes out of the X chart as well. So the new limits by eliminating these 3 control points, that is subgroup 1, subgroup 5 and then subgroup 9, which actually is completely out of the domain of the control chart, we get fresh control limits. And so in our case the mean of means in this case, if we remove the X bars from all these 3 subgroups, are 0.8770. So obviously the UCL and the LCL are getting modified in the case of X chart. Similarly the range, as you can see here from the range chart, because we have completely eliminated the outliers which were there. So this particular thing, this particular range value which was on the sort of edge of the upper control limit, and this particular range value which is above the upper control limit have been eliminated. So that corresponds to a new range bar of 0.0033, and obviously you have to multiply with 2.11 to have 0.0069. So 2.11 is corresponding to subgroup size 5 is the sort of D4 value which is needed for estimating the upper control limit UCL of the range chart. Okay. so which is D4 R bar as you know. So that is how Shewhart has postulated the plotting of the limits. So here this is the new range value, and then obviously if you wanted to again neglect the point which is the 9th subgroup, again the new range comes out to be 0.0026 and the upper control limit comes out to be 0.0055, and similarly in this particular case you can see that the new UCL and LCL have changed quite a bit from 0.8755 and 0.8785. So that is about close to about 0.0030 inches spread in the upper and lower control limit of the X bar. So that is how you keep on modifying and changing the control chart iteratively as the situation may be, and finally you arrive at by removing all the outliers the exact control limits, okay, and then as and when an outlier comes you have to sort of revise the control chart so that the control chart can go for the exact process health and does not really get offset because of the process rejects which are never a part of the system. Obviously if you have controlled, if you have eliminated something from the system, that should not be used as a production data, okay. So that part of that subgroup is completely neglected from being in question. So it is evident from the process that the natural tolerance of the spread is substantially greater. The natural tolerance is actually 6 sigma, which is 0.80084, and the specified tolerance limits here as you can see is only 0.0030. These are the modified tolerance limits as you can see here at the end when you eliminate all the 3 subgroups, this particular tolerance limit. So obviously there is going to be quite a bit of rejection in this case because 6 sigma is quite outside 0.0030 limit, which is actually the process spread, and I would say that the process dispersion has to be reduced in order to keep the process from producing non-conforming components or parts. So that is what about that is all that I have about the X and the R bar charts, which are one of the big references in the industry for studying the process control. We will actually now go to another aspect of control charts, which is about the fraction defectives. So there are certain parameters of quality which cannot be gauged by a particular unit or a value or a dimension or a quantity, and in this case for example let us say visually how a product looks is never quantifiable with any measure. So there can be some kind of a acceptance sampling in that case where we are talking about either a complete elimination by looking at a product which does not suffice to a quality characteristics, or accepting a product based on the perception of the customer, okay. And there we need to understand acceptance sampling, and we also need to understand the probability of accepting a certain product vis-a-vis rejecting, and so we will do some basic revision of the theory of probability before beginning this kind of sampling. And in fact this sampling is also plotted as what is called a C chart, which will come later once we are across all this theory of probability and estimates which would be needed for predicting the acceptance level of a product. So what is probability? So definition of probability is like the percentage chance of occurrence, or maybe let us put it as the likelihood of an event to occur, and as you know the scale of probability is a fraction, so it varies between 0 and 1. So event cannot occur definitely on a trial if the probability of occurrence is 0, but if it is almost certain to occur you can say that the probability of occurrence is 1. So you can take an example, for example a trial is drawing a piece at random from some production line, and that the event in question is that the piece drawn is a defective or a non-conforming one. So let us suppose that the probability of a defective is about 5%. So therefore in 100 parts about 5 parts may not meet the quality specification. So it means that 5% of the times when we draw a random piece from the line it will be defective, and 95% of the times if we draw a random piece from the line it will be non-defective or conforming to the specifications. So, the complementary event is that the piece drawn is a good one, and the probability in that case is 1 minus 0.05, that is 0.95 or 95%. So, that is straight away what probability would mean in terms of acceptance sampling. So, what is the occurrence ratio? So, suppose we have a production process for which the probability of a piece containing at least one minor defect is constantly 0.08 or 8%. So, we then say that the probability is 0.08 for a minor defective. So, now what happens to be to the observed proportion of the minor defectives as we continue to sample. This is observed this observed proportion of minor defectives is what we know as the occurrence ratio, which I will slowly delve into, that what really it means in terms of big samples or small samples. So, let P dash be the constant probability of a minor defective, where the letter P actually means the probability and the prime means the population probability. So, P prime is actually the constant probability of a minor defective as regards the sample. So, in terms of values, what it means is that let us say D is the number of defectives observed and N is the number of pieces inspected or tested. So, the P should really be equal to D by N, this is the sample proportion of defectives. Now, let us see how P equal to D by N behaves as we sample more and more data, or let us say if we increase this N value, then does it change, does it really remain same. Let us just observe that. So, the occurrence ratio of P equal to D by N would tend to approach P prime as we have N going to very large value. Okay. So, the P actually, that is the probability of the sample, would approach the probability of the population of having a minor defect, which is 0.08, as this N size would increase or N would be large. So, we start with say 5 samples of 10 and then samples of 50, okay, and we sort of see what is the percentage acceptance and mention this in a columnar manner. Okay. So, let us look at what they are. So, the sample here is basically given the number of pieces which are the sample, and the D here actually is referring to the number of defectives, and obviously the sigma n here actually talks about the cumulative numbers, and the sigma d here talks about the cumulative number of defectives. Okay. And this way we want to find out what is the occurrence ratio of this population. So, for example, in the first sample of 10, the defectives are 0. So, obviously sigma n is 10 and sigma d is 0, but in the next sample of 10 we have actually picked up 10 plus 10 20. So, the sample size increases to 20 now, sigma n is 20. The number of defectives here is 0 plus 1. So, that is about the increase in the defective, sigma d is 1. And so, when another 10 are drawn, so the sample size would become 30 and the number of defects would become 1 plus 0, that is 2. Okay. And so, this way we are plotting, or we are trying to record all this data of the defectives in each draw or in each circumstance from the total number of samples and total defectives. So, we now calculate the occurrence ratio, which is represented by sigma d by sigma n. As you may see here, that the probability of the sample P is 0.0 in first case, 0.0050 in second case, 0.0667, 0.0750, 0.0600, 0.0800, 0.0800. So, basically what you are seeing here is that as the value is increasing in size, the probability is slowly approaching the probability of the population. So, the proportion defect only tends to approach P dash 0.08. Sometimes it gets closer, sometimes it backs away from P dash. Before the total sample size was 100, for example, in this particular case, the occurrence ratio was below the population size of 0.08, but between 100 and 150, let us say in these two observations, the P dash was replicated in both the cases, 0.8, 0.8, and thereafter above. So, principle that we sort of draw from all this is that we can say that P equal to d by n is an estimate of the constant probability of population P dash. How close the estimate is will depend on the sample size n and the value of P dash and also upon some chance causes. That is how you are explaining the probability of occurrence or likelihood of a minor defect in the sample. So, having said that, there are certain laws of probability that we may need to discuss here, because we will start calculating probability just in about a few minutes. So, consider again the production line producing pieces with a constant probability of 0.08 of the piece being a minor defective, and it is such that each piece is independent of the other produced. So, this means that the probability of the next piece being a defective is 0.08 and the piece being a good is 0.92, irrespective of the preceding piece, whether it is a defective or a non-defective. So, whenever you are drawing sequentially, that would be the probability every time or every draw you make. Obviously, you may fall within the 0.292 category and you may fall within the 0.08 category. The percentage of being within the 0.292 category is much more in comparison to that within 0.08 category. So, now let us suppose that we draw a sample of 2 pieces and inspect them. The outcomes are that the sample may either contain 0 defectives, that means both of them are within the 92% category, or 1 defective, 1 non-defective, or both the defectives, right. So, this is what can be happening, and let us find out the probabilities of this outcome or the event. So, for probability of samples containing no defectives, we must have good piece on both draws. So, the probability of 2 good pieces would therefore be 0.92 times of 0.92. These are 2 successive draws which we are talking about. So, it is about 0.8464. When we are talking about probability of 2 defective pieces, again 0.08, 0.08, so 0.0064, okay. And then if you are talking about 1 good piece, 1 defective piece, so whether it is the first good piece or second, it does not matter, it is basically 0.92 into 0.08 whole twice, okay. So, that is about 0.1472, and so in general, so there are only 3 possible outcomes as you see here, 2 good, 1 good, or 0 good, and therefore, it would be really a summation of all these probabilities. So, either it is 2 good or 1 good or 0 good, and this summation, as we can see also, is actually equal to 1, this being as we calculated earlier 0.8464, this being 0.0064, this being 0.1472. So, this all sums up to be 1, okay. So, that is how it is. So, because one of these 3 events is most certain to occur, therefore, probability of 1 good can be recorded as 1 minus probability of 2 good minus probability of 0 good, and that is 0.1472. That is how the proportionation has been drawn here. So, therefore, probability of 1 good piece being obtained by earlier method is same as this method, and so whether you go by just laying out this logic and trying to calculate based on all this, both the answers converge to the same values, okay. So, the law of probability is really sort of organized as far as the acceptance sampling in this particular manner. Now, I am going to close on this module in the interest of time, but in the next module we are going to talk about several different issues of probability, like for example, if there are mutually exclusive events which are going to happen, then what would be the overall probability in terms of acceptance sampling. We would also be discussing about the example of dependence and equal likelihood of some events occurring, and then again when we talk about large size distributions, how we converge all this probability distribution towards the binomial distribution to estimate what is going on in terms of chance draws when we talk about acceptance sampling. So, all those theories we will get into in the next module. Thank you.